Hello, this is Stefan again from schristoph.online. Today we'll talk about my latest blog post, part of my complexity theory series. This one is about the quadratic wall. Attention costs on the order of n squared in the sequence length, and almost every long context headline of the last few years is really one algorithm story about beating that wall. Here is where the n squared comes from. In standard self-attention, every token computes a relevant score against every other token, which is an n by n matrix. Building and applying it is quadratic in arithmetic, and the score matrix itself is quadratic in size if you materialize it. Double the context and you roughly quadruple both. That single fact is the wall. This diagram makes the wall concrete. With n tokens, you form an n by n matrix, so both the arithmetic and the score memory scale with the square of the sequence length. The whole point of naming the variable n is to see which techniques change the exponent on it, and which only change the multiplier in front. When you meet a quadratic, two moves are worth separating. One improves the constant factor. Same big O work, but each unit is far cheaper, usually by respecting the hardware. The other improves the asymptotics. You drop the exponent itself, which bends the curve, but almost always costs you something the exact algorithm gave you for free. FlashAttention computes exact attention, the same numbers, so its arithmetic is still quadratic. What it changes is memory. It tides the work so scores are formed and consumed in fast on-chip memory, and the full matrix is never written out. Working memory drops from quadratic to linear, and traffic to main memory falls sharply. It is an asymptotic win just on a different axis than the one people usually watch. You might ask, if FlashAttention does not change the big O, why does everyone use it? Because asymptotic class and speed are different claims. On real accelerators, memory bandwidth is often the binding constraint, so cutting data movement and peak memory is exactly what made long contexts usable. Same big O, very different speed. The asymptotic attack is where the interesting architectures live. Sparse attention restricts which token pairs are scored, linear attention rewrites the operation so it never forms the matrix. And state space models like Mamba carry a fixed size state forward through the sequence, updating it token by token. No n by n matrix is ever built, so for a fixed state width, that is linear time sequence modeling. So are state space models strictly better? Should you just switch? No. And the post deliberately does not say so. A fixed size state compresses the past, so information a full attention matrix could reach directly can be harder to recover. Whether the linear time win is worth it is task dependent, which is exactly why hybrid designs interleave both kinds of layers and why the field has not crowned a winner. Here is the complexity lens that keeps this honest. Several different quantities all get called cost, and they do not move together. Arithmetic, memory movement, peak memory, latency, and on a metered API, the bill naming which one a technique changes is the whole discipline. FlashAttention moves memory, not arithmetic scaling. State space models move the arithmetic, a price cut moves only the billing coefficient. And there is a move older than all of these architectures. Reduce n. The cheapest attention is the attention you never run because the prompt was shorter. That is one thing retrieval buys, sending only the relevant passages instead of the whole corpus. It is not free, so whether it pays is an end-to-end question to measure. But it composes with every architectural improvement rather than competing with them. So how does this land on AWS, on Amazon Bedrock? Favor models and context patterns that match your real sequence lengths and lean on retrieval. Treating long context support as a capability you use rather than infrastructure you build. If you self-host on SageMaker AI or EC2, the lower level levers become yours, and purpose-built silicon like Trainium and Inferentia makes the remaining work faster. The silicon does not repeal the n squared, it widens what you can afford to run. This is the primary source for the memory story, the FlashAttention paper by Dow and colleagues. It is the one that showed you can compute exact attention with quadratic arithmetic, but linear auxiliary memory and I/O optimal traffic to high bandwidth memory. Worth seeing in its original form. And this is the source for the state space side, the Mamba paper by Gu and Dow. This is where the linear time claim and the roughly 5 times inference throughput number come from. Reported by the authors, along with the content-based reasoning trade-off, the post is careful to attribute honestly. Thanks for listening. I hope this was helpful. If so, you can reach out on LinkedIn directly or head to my blog at schristoph.online. Let's keep in touch. Take care.